So far in the first two lectures, we have created a Rust workspace, and first we set the environment to build and compile for the host machine, which is an x86. Then we configured the Rust workspace for cross compilation to compile for an RISC-V target instead of the host target. And this is the lecture 3, and here we are gonna see how to add RISC-V assembly on Rust workspace. So this is where we left in the previous lecture, and I did make some changes. So I'll just run through a few of those changes. So I just upgraded my cargo binary, and it prompted me to change few things. The first one is, so far I had the config file inside the .cargo named as .cargo/config file, but once I upgraded my cargo binary, it said that the naming has to be config.tyml, explicitly mentioning that this file should be of the tyml format. But there isn't any change inside the file content, but just change the name. And the second change is on the cargo.tyml file, which is on the root of the Rust workspace. Since I upgraded my cargo binary, it asked me to choose the resolver either with value 1 or 2. It looks like if the cargo binary is with the version which is before 1.57, cargo might use a resolver 1 to resolve those dependencies, and since I upgraded, it asked me to choose 1 or 2, and I just added this one key value pair, which is resolver equal to 2. So this is a second change. A third change is I just copied my linker file, which I plan to use for this. So this linker file I created exclusively for the FE310 SoC, which is there in the Hi-Fi 1 revision B board. So this is the memory region, which is RAM. This is on-chip RAM with starter registers and size. And the off-chip memory starts from other off-chip flash, starts from this address with the length of this. Okay, and I have created few sections. One is to keep the text, and since we are building a high-level language like a Rust, it might have a read-only data and global data, which is BSS section. So I don't know how much of this would be used, but anyway, I have created those sections, and I have mapped all this to the off-chip flash memory region because the plan is to boot from flash. And finally, to provide a linker variable which I can access from the boot code, and this variable is set with the size of 1024 from the RAM, so origin of on-chip RAM plus 1024, so that the stack can grow up to a depth of 1024. Okay, so these are all the three changes since the last lecture. Now let's build on this. So as I said, the main goal in this lecture is to add a RISC-V assembly, which means this binary crate, we are going to add some boot code, which is a minimal boot code and RISC-V assembly, and then jump into the Rust code. So this is the binary crate, digital_clock. Now inside the source, we have the main.rs file. And so there are many ways you can add assembly code in Rust. One is, I'll just type here, one is ASM macro, okay, and see how you can use this. And other one is global_ASM macro. So if you see here, so when I added this ASM macro, you can see that's getting included from the core library. So for global, if I plan to use this macro, then I should just include global underscore ASM here. But there are one more option, which is like to, so this is one option to add any assembly code inline. So the major difference between this and this is that, as the name specifies, so whatever that's put inside this global ASM macro would be global. That means that functions within this would be emitted and it can be accessed from, it will be visible to the linker and other Rust code and so on. So that's the only major difference between these and this. And other one is this is mostly you can, like a block of assembly code, and this is like you can add a small RISC-V instruction here and there. And the third option is to create a new file, and you can call that as boot.s or whatever, some assembly, and you add all the assembly code here, and then you have to include using include underscore str macro underscore str. Okay, so I'm just writing it here so that you can search and choose one of that, but what I'm gonna use here is the global ASM. Okay, so let me delete this and take it back to the original state. Okay, this is how it was, and let me create the, you see, the moment I enter, you can see the global underscore ASM as being included from the core library. That's good. So here the entire assembly goes inside this within the quotes, and let's create a function. So this is a typical assembly syntax. Let's go. Two things in very first, let's disable the machine external interrupt, because when we are setting the boot code, we do not want any external interrupt to interrupt this boot code flow. And second one is to set the stack pointer. So these are the minimal things that you need to set before jumping into any high-level language. External. So this one I'm disabling to set the boot code, and later I would enable, but the stack pointer is needed because the high-level language, before you jump into that, the stack should point to a proper location. That's why in the linker file I exported this variable name so that I can use that here to set the stack pointer to that particular address that you can do. There are a few assembler directives. So this would get the higher upper bits from the address, which is pointed by the start address plus 1024 in the RAM, which means this value plus 1024 should be the value that SP or stack pointer should get populated with. And then we can just jump into, let's call this as Rust entry. and we can just jump into Rust. Okay, and then we can enable this, do more settings inside this Rust entry, and then we can enable this external interrupt. But let's see, let's build now. Clean. Now let's see if it is, we can read the binary file and see if it is as we expected. So object dump, so digital flock is the binary crate, and so it looks like there isn't any objects. Okay, that might be because if you go to the configuration file here, so we are building for this target, but then Rust by default would have the, so none of this function is called anywhere or used anywhere, so it might have just compiled all those out. So what I'm gonna do is, let's create this section, which is and here let's add some Rust flags. So this link arg is to set the linker file, custom linker file, and so with the -t flag. So that's it. And the another flag which I want to set is link dead code. So the link dead code flag is, you can enable so with these two Rust flags, or with these two configuration passed to the RISC-C and the LLVM. So this is just to mention to link with this linker file, because by default there would be a linker file that would be used. We would not know the memory map and which processor that is, so that's why I just want this code to be linked against this linker script. And this flag would just enable the dead code to link dead code. It is not just that like the compiler warning, you can, if the function is not called, it's not like that. Even when we set this flag, even if the function is not used anywhere, still that objects would be present in the binary. So right now, if you see this object dump shows that the ELF is an little Indian RISC-V target, but however there are no objects in it. That's why I just want to enable this, enable to link a dead code. Now let's build again. What is an undefined simple Rust entry? Okay, for this to be visible, extern -c. So this should make it. And one more thing I missed, prevent it from mangling, because hash. I think that should be sufficient. Let me try that. Yep. So by default, the mangling would be enabled. In that case, this name would be suffixed or prefixed with some other text. However, if you, I have set, I enabled, set this function to be not mangled so that it will be visible, so that this jump rust underscore entry function name and this one would match. Okay, so now we have built. Now let's see the object dump if there are any objects on it. Okay, now you can see this. Let me pull this up. So that's our boot code, and which starts from this is the starters of the flash. So right after reset, if the processor is set to boot from flash, it would jump here, and first the external interrupt would be disabled, and you can see the assembly instructions here. The stack pointer would be set with address as this is the 80000 plus 102 for the depth of the stack, whatever we want, that has been set. And then it jumps into the rust entry function. So this is the address of rust underscore entry function. So after this it would jump here, and this is the loop. You can see jump again in here, but I do not like this address when it is not aligned with the power of 2. So what I'm gonna do is, so this jump instruction are available in 2 variants. One is a compressed, which would take only 2 bytes, and the other one is uncompressed jump, which would take 4 bytes. I do not want to enable this compressed instructions now. The reason is the start address or the address of the functions might not be aligned with the power of 2 and times 4. It might not be aligned with the times 4, and sometimes it can really cause a problem, because few of those, as we will see later, that few of those function address should be aligned to the address multiples of 4. So what I'm going to do here in the configuration is to disable a feature called, okay, so each target for RISC-V target, there are many target features. Like in RISC-V, there are multiple extensions, so that those are all the target features. And this would what this target feature is set is to remove the -c, to remove the compressed extension. So now if I clean and build again, and let's dump the objects. Now you can see the jump order. So the instruction has been made as an uncompressed, which is 4 bytes. Since this is RV32, the addresses have become, and the instructions have become 4 bytes. So there will not be any address misalignment here. Okay, so that's it. So now let's see the code here. So we are able to add some basic boot code, and then it jumps into the Rust entry, and all the configurations for the compiler and the LLVMs and the linkers are all passed through this .cargo/config.tyml file, and we have added the linker file, and most importantly, the binary or the executable that is getting built is in the proper order as we expect. So if you go into the linker file, I would have set this entry as __ boot, and at the same time I have also forced to keep the boot section at the very first, which will be the starters of the flash. That's this one. Okay, so in the next lecture we can writing some Rust code to configure the clock and to need more needful stuff to bring up the processor.